We would now like to put together all of the pieces that we've been learning about. A resistor, so let's add a resistor to our circuit. Let's add an inductor to our circuit. And let's add a capacitor to our circuit. And now we have the driven RLC circuit. And what we'd like to solve for is that it's fixed. Right now, our angular frequency that we're driving the circuit at is fixed. And we'd like to solve for the current response, I. So now let's look at what we've done before. So all we have to do is get the complex impedance, which has the resistor. We have two imaginary pieces, the inductor, omega L, minus 1 over omega C for the capacitor. And again, we'd like to get the amplitude of this complex impedance. And so that's the real part squared, the imaginary part squared to the factor 1/2, and the phase here, which is the inverse tangent of the imaginary part divided by the real part. And what we saw, the same analysis as before, when we write V equals Z equivalent I, then we have V naught e to the I omega t equals the amplitude, the phase of the complex impedance, the amplitude of the current, the oscillatory part, and the phase. And so just like all of our other cases, the amplitude of the current, I have to be a little careful here, that's the amplitude of the oscillatory voltage divided by the amplitude of the equivalent impedance. So that's V naught over R squared plus omega L minus 1 over omega C squared to the 1/2. And the phase, again, the phase factors have to cancel. E to the I delta times e to the minus I phi has to be equal to 1. Delta has to be equal to phi. And therefore, this is equal to delta, which is the inverse tangent of omega L minus 1 over omega C divided by the resistance. And we see the beauty of using the impedance is that we were solving a fairly difficult differential equation, that L di dt, that's the voltage drop across the inductor, where we're using this modified Kirchhoff's law over the element for the capacitor plus the resistor is equal to V of t, and I, we can say here, is dq dt. And that's a hard equation to solve if you want to use sine and cosine functions. It's very messy, cumbersome. This is a beautiful way to solve this problem.